We always requested Professor Sampathkumaran to be a part of the IMSC 60 Distinguished Lectures series. But since that program is over now, we have to do it separately. So I just wanted to mention that this is a continuation of that, which we couldn't do it that time, but it's very great pleasure that we could have you here.
Okay. Thank you very much, Professor Bhaskaran, Professor Sayanthan, uh, for inviting me to give this very distinguished lecture. I'm really very honored to get the invitation from IMSC to give a distinguished lecture here. But unfortunately, I could not come, as I said, due to some personal reasons. So I'm glad that at last I made it here. I'm very happy to be here. And I would say that it's a great institute, and yes, several very eminent people in this place. And it's always be a pleasure for me to be here. During the last 15, 20 years, I'm almost every year coming, I mean, very regularly, thanks to the hospitality of Professor Bhaskaran, who has been our good friend of TA for the past 5 decades. It is not 1 day, 2 days. Of all my senior colleagues or anybody used to come and interact with him. It was a great pleasure to sort of have an associate with him. I hope it continues for many years to come. And let me wish all the best to all the staff members of the institute for a very glorious future. Thank you very much for that. Okay. So, why are you studying? Why is it basic science important for that? To look at the, that these basically electrons are basically also called rarer systems. Why the rare? The rare terminology came because 100 years ago, you have to really mine those things. It was the very rare material. Therefore, the elements are called rare elements. Rare elements, they come from earth, of course, like many other metals. And rares, so the problem is that initially it was rare. Now it became a little bit more abundant. As more and more you mine, become more and more abundant. And people wonder why the terminology rare should be retained. But for historical reason, that terminology rare is being maintained. But now it is really going to become rare. The reason is that if you look at, it's considered the vitamins of modern industry. If you look at, I just listed down various things like cell phones, you forget about the old utilities, new utilities, cell phone, computer memory, rechargeable batteries, flat panel television, superconducting magnets, magnetic resonance imaging, glass additives, fluorescent materials, light bulbs, wind turbines, look at so on and so forth. Also, magnetic refrigeration. Refrigerator may be one day replaced by these materials because you get rid of all the freon gas to have to save the say Earth's layer of xenon. So the reason is they generally attributed to various interesting physical chemical properties, special properties of the rare earths, and it's now recognized that the energy consumption is really lower compared to many other materials. It turns out they are lower, and therefore greater efficiency, and it also helps in miniaturization. Small trace is enough to sort of change the properties, the miniaturization of gadgets, durability, thermal stability, and all these really matter a lot when you talk about applications. Therefore, is being recorded, I should not say that which country, because we get international politics, but there is a tendency for some countries in the world to accumulate this, I mean, very silently, so they can dominate. You can make out which countries are. They dominate the world's economy in future. So this is going to be a very crucial material for the future of the mankind. So this is the reason. Therefore, the growing realization there's a need to understand the properties of these materials. Okay, so okay, now you cannot make out hidden tail of that. By the way, I may just flash the transparencies and there'll be some graphs. Forget seeing the graphs, forget seeing it, just because only to me, I'm going to tell you like a story. I mean, a colloquium, there is no point producer showing all the data, everything, because still for the benefit of some experts, some figures you will find here, but just only listen to me. It's just a story of electron physics. So you could see a number of phenomena, but from I'm giving listing down 1960 or have been discovered from time to time. Only some I listed, not everything, and some I'm going to explain today in my talk. So they present very exotic situations in condensed matter physics. Therefore, even not only from the application angle, also from the basic science point of view, they have been presenting very interesting situations, and that is the reason these compounds are the materials are very important. Okay, what are rare earths? Sorry for this audience, I should not say that, but still, I mean, the periodic table, these are the elements from atomic number 57 to 71, the lanthanum to lutetium, they are called rare earths. And the electronic configuration is contained the xenon ion core, and then you have xenon ion core, and then you have the core shell, supposed to be a core shell. This is what I'm going to contest in my talk today. Core shell 4Fn, 5 6 plus 2, they are the outermost electrons which go out for bonding. So therefore, if generally these are the electrons which go out for bonding, what is varying is the F electron number if you go from lanthanum to lutetium. Therefore, if he says a compound is trivalent, that means these 2 electrons are gone out, because this is not supposed to participate in chemical bonding. I'm going to change this statement later in my talk. That is basically the crux of my talk. So, okay, this is considered to be trivalent, and historically, therefore, valency, if you look at the textbooks, MSc, BSc textbooks, you will find that valency has been defined in terms of 4F occupation number. So, if I say, for example, samarium is 3 plus, then 3 electrons gone out, that means the valency is 3 plus. Okay, that was generally the belief. Okay, so again, as already mentioned, we have to acknowledge Professor Vijayaraghavan, who actually initiated this rare earth research in this country, TIF4. In fact, TIF4 is only dominated this field for decades. We made, again, I don't want to be, let me not be modest. TIF4 made in this field very important, very crucial, pioneering contributions, which really put India in the world map. I'm using stronger words, which I'm personally very proud of. And I'm also party to it. So in my talk, what I plan to do is I just going to highlight some 1 or 2 such important contributions. Apart from highlighting the landmark discoveries in this field, some of the landmark discoveries from our own labs, which way we made a difference to that. You can always ask a question when you have do research, when you retire, you have to ask a question yourself, which way my work has made a difference to the field? You know, that is a very important question to ask ourselves every stage. I mean, every work need not be of great quality. Okay, you publish a nice journal, but you say, okay, this particular paper, particular work made a difference to the field. So I would say we can say there are quite a good number of results which made a difference to the field. Some I will point out today. Okay, so I would like we should remember Professor Vijayaraghavan and acknowledge him for his contribution.
5d6 is that 3 or is it like from the end?
No, it's from here. If these 3 go out for bonding, valency 3 plus. Okay. This is the 4F shell was not supposed to participate in bonding anyway. Yes. Yes. No. As defined, sorry. In terms are not correct. As defined in terms of, by that I mean that if you know the 4F electron count, you can tell what the valency. Is a measure of 4F electron number. But maybe English is not correct. Valency has been defined as a measure of the 4F occupation number.
So the valency can go up to 14.
Cannot go, because all the 14 cannot go out for bonding. Valence basically 3. Valency remains 3. If these 3 go out for bonding. However, in some cases, like I'm going to make next transparency, samarium, europium, this electron stays back, only 6 has to participate bonding, then valence becomes 2 plus. Again, this is a very open question. Therefore, there are theoretical atoms. Some rare earths, I mean, in some cases, for europium and samarium, this stays back, only this will go out for bonding, then you have 2 plus. When you come to cerium dioxide, cerium O2, I mean, I'm going to contest that, but I'm saying from the chemist's angle, cerium, 1F electron, you have 4F1. So this F electron also goes out for bonding. They become 4 plus. Ytterbium, 2 plus and 3 plus. So some of them can have multiple 2 valencies, depending on.
So is it correct to say then which goes out for bonding?
Yes.
Is modulated or also controlled by the 4F electrons?
Yes, valency is controlled by, that's why valency is being controlled. What is the 4F occupation number? I mean, that was the belief. Okay. Now, I'm going to give a confusing statement and I'll explain to you. That is how the field has developed. Okay. What? 7 is half filled, gadolinium. No, they don't. It doesn't come out. It is stable. I think that is what generally found, either close to unfilled, half filled, and fully filled. They try to remain stable. Okay, that statement is accepted. So I'm going to say that gadolinium is very special, as you said. It's everything stable. But that is where we made a pioneering contribution, which is being picked up after 2 decades from the current literature, that it behaves like cerium on the face of it. But there's a new physics in that. And we pointed out 2 decades ago. That's what I'm going to point out. Talking about exotic physics and which way your results made a difference. This is one of the results. Even gadolinium, where you expect that you don't expect anything interesting, everything stable, you have problems. I'm going to show one example without going too much of detail. Okay, that's fine. No. Oh, I'm coming to the next transparency. Okay, so this is what I'm putting same thing differently. The electron count is changing here. The spin quantum number, L orbital and total, and then it's called Landau G factor. These are not very relevant for the talk today. And this what you should remember. This may come up in my discussion. I may mention what's called Dijon's factor. Dijon was probably got Nobel Prize about a decade ago. This fellow from France, he made all kinds of systematics by looking at the properties of different material. And this is the one of systematics. It's not based on any theory. So he found out that the ordering temperature, spin disorder contribution, some of the properties scale with a factor called Dijon's factor. This is after him. Fact is called Gj minus 1 whole square J into J plus 1. There is no theoretical basis for that. So he found out by looking at it, everything should scale with that. This is under the assumption that 4f electrons are localized. 4f shell, as I mentioned, it doesn't participate in bonding. Then this is valid. Okay, and in some cases, in some family of materials found to be true, in many family of materials not found to be true. I mean, now it is recognized. Okay, these are. Pardon? No, yeah, right. Okay, so you got a price, a node price, sorry. Right? Dgen. Okay. Gj Landau G factor. Okay, you don't have to worry about for my talk. Landau G factor. It is derived from L and Sj, Landau G factor. This is atomic physics. Since I booked out from a book and I just put it, what is relevant for you is this. This is under the assumption that the 4f shell is localized, does not participate in bonding. So since you asked a question, when it comes to cerium and terbium, they can also exist in 4+ state. You have Tb3O4 and the cerium dioxide, cerium tetrafluoride. In addition to cerium sesq, cerium 2O3, you can have, they have more than one valency. Similarly, samarium, europium, terbium, ytterbium can be in 2+ state. In other words, one of the d electron it comes back to 4f shell. D electron comes to 4f shell. This is a drama that is going on. For the 5d electron, 5d can either go out or come back to 4f. The alpha electron configuration changes. So it depends upon the energetics of the system. In total energy of the system can vary. Okay, so now this is a very fundamental. This lunchtime you asked a question. They are very fundamental graph. When you say it doesn't participate in chemical bonding, for example, gadolinium in the middle of this series, how does it 4f orbital looks like? These weights, this is a radial distribution function as a function of the distance from the nucleus. This is the half of interatomic distance, gadolinium distance. You could see here that the 6s is a bonding, is a gone out. 5d also gone out. Now we have 5s, 5p are essentially outermost orbital. They are filled. They are filled. Now the 4f is the one which contains unpaired electron, 4f7 configuration. So these are well within the ionic core. This is a radial distribution function. So therefore, you naturally expect the 4f does not participate in chemical bonding in any material. Okay, so this was a belief till 4 decades ago. Okay, so just for comparison, how it was believed that this is the core like, but when it comes to actinides, a little bit more extended than this. When it transitions from 3D, they are really practically, for all practical purpose, they are almost outside. Okay, of course, there are some systems where they behave like localized. This is roughly the picture, just for increasing the localization of the orbital responsible for magnetism. Okay, so now therefore, you could see that the topic of great research during 5 decades, if you want me to summarize in one line, what is the problem? Is that there is a drama going on. Sometimes the 4f electrons look like localized, sometimes they look like completely delocalized. And this manifests in different ways. And I cannot explain everything in my talk. Some I will mention that 4f localization, delocalization phenomena, which is occurring for the past 5 decades, they be extensively studied at the beginning of rare earth series, for example, cerium. Cerium is the most extensively studied, but it is believed that when you come to other rare earth members, it's not that bad. But we have evidence to show that your problems, even when you come to freezdomium and eudomium, which I'm not going to explain. I'll give maybe one example. So these systems are also called heavy electron system. We discussed at table today. I will explain why they are called heavy. And this is central stage of condensed physics or material science research today. If you want to summarize in one line, this is the bottom line. All the phenomena you have to study are connected with this competition between localization and delocalization of the 4f electrons. Now, what I'm going to do, I'm going to very brief historical, having given introductory remarks about the textbook thing. Sorry for being too elementary, I hope you don't mind. But I thought it's very important being colloquial to mention that brief historical perspective. Now it is being realized. I think our group is the first one to point it out. Even the localized 4f systems like gadolinium are exciting. I'm going to give only one example, which might difference the field. Now, don't read it, since I want to show you for a different reason. You cannot read anything. See, this field of research actually started, credit goes to Boltzmann in 1920s. You know, Boltzmann is the pioneer of high pressure research. He was studying different materials. You are trying to make, different kind of high pressure cells and try to study all the materials on Earth under pressure. Okay, so as I told you, I'm not going to discuss too much of physics now. I'm going to tell you a story. Bridgman anvil, you put Bridgman, right. So he, for example, studied cerium metal under pressure around 6 kilobar. He found a transition. So I left it like that. Subsequently, the other group, he measured the electrical resistivity. Other group, for a period of 3-4 decades, different people tried. Some people could confirm it, some people could not confirm it. The reason in those days, it was not easy to get high purity cerium metal. So these people, after something like 30-40 years, Lawson and Tan, they got called off some relatively pure cerium metal. They confirmed, they measured lattice constant, they confirmed. Here there's a huge change in the lattice volume. These are all FCC cubic, lattice volume around something like 6 kilobar. So okay. Now the interesting thing is, look at this is a 2-page paper. It's published in Physical UB 1949. Today, if you send a 2-page, they're not even abstract. You don't even abstract there. Okay, you have only one or two references at the bottom. Now it look like a newspaper item, and then they somewhere in the middle say, as a result of stimulating discussion with our colleague Zakarian son, you normally put an acknowledgement. It's written in a very funny way. If you send a paper like this to APS journal, the watchman himself throw the paper out of the window. It's a fact. Things are done I want to tell you that the emphasis was more on science, not on today. If you want to send one journal to another, same paper is rejected another journal, you have to change the format. You have to work for 1 week to change the format. You want your comma is missing, full stop is missing. That was not the case. Just 2-page paper, not even abstract. It's like a tea table discussion. They summarize the results. Okay, we find it. Okay, we discussed with Pauling and Zakarianson. They say that maybe their valency is changing from cerium 3+ to cerium 4+. Okay, why there's a volume change? Maybe 4f electron has completely gone out under pressure. They left it like that. This is probably the first time it was realized. Same material can undergo a F electron total transfer. They assume total transfer. Okay, so they left it like that. Subsequently, good number of people picked up this cerium metal, tried to study thoroughly magnetism, transport property, everything. What they found something very funny, that if you look at the magnetization, you know, if an electron goes out, if F electron, there is no magnetism left, ideally. So what people found is that there is still some magnetism left, but it's not same as what you expect of or upon something intermediate between non-magnetism and magnetism. This confused a lot. And then high temperature, it behaves like magnetic. At low temperature was not behaving magnetic. The polyps was susceptible at low temperature. Okay, so these are the confusion for some time. And then, okay, this is a very interesting phase diagram. Okay, I don't should spend my time on it. This cerium metal is very interesting phase diagram as much on temperature and pressure. Let me not spend my time. Okay, the real challenge came in the real turning point in the field was the paper by Jayaraman. You know, Jayaraman, I think the recording, I should not say that. Very interesting. Jayaraman gave a talk about 3 decades against TIF4. I mean, a colloquium, a special colloquium. By the Jayaraman is around 94 years old. He's a very pioneering worker in quantum physics. And he's right now in the United States with his daughter, I'm told. He's a very simple, nice person to interact, very humble person. For music festival. Yeah, a very, very simple personality. Anyway, he again is a high pressure expert. He used to study many materials. By the way, it's not record, but I don't want to mention, I'm putting very, very mildly. Jayaraman is the nephew of Sir C.V. Raman. Jayaraman joined Sir C.V. Raman for doing PhD in Bangalore. And one fine morning, he ditched his uncle and decided to go to the United States. That really irked C. Raman. Okay, apparently he told him some strong words, which I know what I still remember, but I will not mention in this talk. It was very wild at Jayaraman. He left, and but finally, I mean, right or wrong, we don't have to question that. He made a very impressive contributions in Bell Labs after. Yeah, it's another book. No, he has very high regards for Raman. Very high regards for Raman. I mean, so for his own reasons he went, but he published very beautiful results on different materials in quantum physics. And this is what he did is he took samarium chalcoinite, samarium sulfide, selenite, telluride. They're all semiconductors, black material. So what he'd applied pressure under 6 kilobar, it becomes golden color, golden yellow. You know, you start with a black material and apply pressure 6 kilobar. In fact, you don't even require 6, you don't go pressure cell. You take the material, you just put it in your Pezilan mortar, just grind it, become golden yellow. That's all the pressure required. Very small pressure, very small. You can see with your own eyes. And it'll come back, when you release the pressure, it'll come back to black. Okay, same thing can be induced by chemical doping. Instead of semi-cell, you put a little bit of yttrium in that, reduce a cell, it'll become gold. You start with the black material, you end up with a golden color. So he found it. The paper is published in Physical Letters in 1970. This was again a landmark result in quantum physics. You could see the first order transition at 6 kilobar. But the people tried to, including Jayaraman's group, people tried to study again depth of this material, and they found it behaves exactly like cerium under pressure. So in other words, high temperature, the magnetism behavior looks somewhat intermediate between 2 plus and 3 plus. High temperature looks like a localized moment, and low temperature, it appears there is no magnetism. It is very funny. So this was not understood, but the first time, this group of people, Maple and Wolleman, came out with an interpretation for this anomalies that on one hand, they sudden change the volume, sudden change the properties, the lattice constants are not matching with what you expect for complete transformation, and you find something intermediate magnetic behavior. So they, at that high temperature, you have magnetism, or low temperature, you don't have magnetism. How do you reconcile all these things? And these are the people, a very eminent scientist. By the way, the B.T. Matthias, for the physical youngsters, 5 decades ago, he was the very well-known person for superconductivity. So he studied all the materials on earth, on metals to look for high temperature superconductivity. He gave up. And then he said, He said before he died, apparently there is a last statement he made before he died. He died of heart attack at 60. He said, okay, I tried all the metals. Please try oxide metals, oxide materials. He's made that statement. This Ullaman told, Ullaman is no more, he mentioned that. So he actually he lived, if he lived longer, probably IT superconductor probably discovered even before. So the fellow was very serious. See, he produced a lot of very eminent people. These are some of the, Maple is right now, again, from more than 80, he's at UCSD, but unfortunately he's no more. He's a very good friend of TFR group, because our paper, I published in PRL, went to him as a referee. He's a leading person. And that's why he came to know us. He even visited TFR afterwards. So anyway, they said that this can be understood because of, they coined the word intermediate valence, and they forcefully degonized, and they tried to explain in terms of some model. So what Fiddle Anderson model at that time. Yeah. Yeah. Ullaman is well known for that. Correct. At TC, it becomes paramagnetic and then become diamagnetic. It's called Ullaman effect. Yeah. I see. Okay. Yeah. It's called Ullaman effect. That's true. Many youngsters, when ITC field was discovered, I mean, at the transition temperature, it's susceptible to diamagnetic. Instead, he found an upturn short wave, and then this began. So that's called, he discovered for the first time. It's called Ullaman effect. So anyway, so these are the people. He said that you have to coin a term called intermediate valence. It's neither 3+, neither 2+, or not 3+, stays somewhere in between. And how does it become non-magnetic? They produce some theory, and they are low temperature, it becomes non-magnetic. In fact, put it theoretically, there's a transformation from, you can say, explain better, transformation both science and statistics to Fermi-Dirac statistics as vary the temperature. Well, even statistics changes, but the same system as a function of temperature. So anyway, so therefore, for the first time I realized the valency can be intermediate between two valence states. Not a simple valence chain, somewhere intermediate called, although the fluctuating, electron goes out and comes back. Not only intermediate, it goes out and comes back. How do you get intermediate valence? The time average is fractional. If on a time average option, sometimes measure photoelectron spectroscopy, you'll see both the valence states. So the time scale is involved. You measure through Mossbar, which is flow technique, you will find an average. Susceptibility is a sort of average, you find that. Okay. So it depends upon the technique which you use. I don't have time to explain all these things. If you're using a very fast technique, you will see both the valence states. If you see a very slow technique, then you will see the average one. So that is how these things were confirmed. Yes. Yeah. So I just want to flat one transparency. Basically, my thesis work in 1970s. We discovered a new material, europium, probably second material, that in europium system, that this compound, look at it here, susceptibility of this compound is this one. Scale, you have to be careful. This is a divalent system. You have to look at this side scale. This is the trivalent system. Look at this scale. For our compound, you have to look at it, the divalent, you look at this side. So therefore, this curve should be lying somewhere here like this. So in this compound of interest, you find the intermediate susceptibility. And not only there's a huge drop in susceptibility here at some temperature. And this you forget that upturn, this is due to impurity. Later on, we got better material where virtually negligible. So susceptibility becomes basically constant at low temperature. So as you said, you wanted to know valency, you can determine valency from these numbers. Using susceptibility of this and using susceptibility of trivalency and divalency, you get the valency here. This is called the valence. You could see here, almost goes from 2+ to almost 3+ as a function of temperature. Okay. That means that it just goes out, you're losing it, participant bonding, and comes back. This is a fractional, this is called fractional valence. And this is basically isomer shift for Mossbar. I don't know, for the very young people who are not aware, Mossbar technique is a nuclear technique. When you measure the parameter called isomer shift, I don't want to explain what the technique is. Isomer shift, like chemical shift and no more. The isomer shift measures the s electron density at the nucleus. This electron density depends upon the how many electrons you have. See, basically, outmost electron you have, 5s. That electron density you will feel here. So this being shielded by the number of 4 of electrons here. So this is a measure of 4 of count. I mean, approximately. And for europium, this is the best technique. You could find isomership. If it is trivalent, should be close to 0 with reference to europium trifluoride. If it is divalent, it will be somewhere here, isomership. For this compound, you will find for the stable valent compound, it will be practically temperature independent. Okay, that is established. But in this compound, you could see here almost 3 plus state to almost 2 plus state, very huge valence change, huge change in this range. So you can determine the valency from this isomership. This takes 3 plus reference, the 2 plus reference, and use this plotted here from what you determine susceptibility. So there is a fairly good trend in this. Yeah. Yeah, exactly. Yeah. Yeah, correct. And it, by the way, this could be made first order by a little bit doping by a little bit of gold. Yeah, as function of pressure. Oh, that is a valence change. That is a fractional way. It doesn't go to full valence change. It goes to fractional valence change. It jumps. It becomes 2.6. From 2, it becomes 2.6. Roughly, I mean, plus or minus experimental error. Okay, this is a very pioneering work from India. And if you look at journals, Japanese people are still following their compound. For 5 decades, it's still attracting a lot of attention. The moment we discovered, I mean, I became famous because of this compound. I must say that. So we visited Bell Labs, IBM, Xerox follow, everywhere, many institutions, people follow it up, this particular compound, and attract a lot of attention in this. Very unique compound. This remains to be unique even today. No compound has been discovered afterwards, which behaves better than this particular compound as far as europium concerned. Then another compound, europium nickel to phosphorus, you could see really it remains intermediate valent. It does not go here or here. Now apply pressure, it goes towards this, but not as function of temperature. The one compound which was discovered before our compound, europium compound silicon by a Israeli group in 1973. So you could see, of course, now some more compounds are known now, but there's nothing comparable to this. It's a very unique contribution from India in this field. Okay, this is a paper which I published in Physical Letters. I don't want to go into the detail. I just want to tell you that we are europium valence, intermediate valence. You don't have to look at this site. You don't have to look at copper site. And we have proved through NMR, nuclear magnetic resonance. You look at the copper nucleus, and it can tell you something about what is happening in europium site, because you are measuring electric field gradient. That is how we have proved that even the charge state is changing. It goes from 2 plus to 3 plus. Charge state is changing by looking at the electric field gradient at the copper side. This paper was the first work of this kind in this field. This paper went to Ullaman for reviewing. He wrote to us that we are very happy to see the paper. That time, a lot of discussion about, whether the charge state is changing, not changing, where is the 4f electron going out, all kinds of questions. This is a very satisfying work in that respect. It is temperature dependence on copper nucleus. When it comes to this compound, there's a very huge change in electric gradient on the copper side. Okay, let me skip that. Now, therefore, when people are trying to discover newer and newer materials materials where there is a valence change or the delocalized phenomena, people are studying serum compounds, and there was a problem in 1980s. The problem was, again, same Dieter Ullman, which was referring to Ullman effect, with a pioneer in the field. He was from Cologne. He was reporting several compounds. He found that spectroscopic technique, there is even if you look at cerium dioxide, cerium ruthenium oxide, which are supposed to be superconductors. Superconductor means magnetism cannot coexist, at least those days. So even cerium dioxide, which insulating material, if you tell a chemist, you would say cerium is tetravalent. That means there is no 4f electron. Okay, and this fellow found that you cannot find even a single material where valence 4f electron completely goes out, including insulators. Cerium. He said cerium dioxide is not tetravalent. The title of the paper is there is no tetravalent compound. That is the title of the paper. There is second conference in this field. First conference 1976. Second conference when Santa Barbara Anderson was there. he boldly proposed it. There is no tetravalent cerium compound. Now everybody laughed at him. I mean, this must be crazy because it becomes so famous, you can say anything he wants. Now, some people believed it because Wellman says there must be something behind it. So people took it seriously and pursued it. The cerium dioxide, can it be tetravalent or not? And a systematic study has shown, indeed, that there is cerium 4f electron. There is an electron on the 4f when you come to cerium dioxide also. So, and how does it came? This will look at spectroscopy study. What is that called? You don't know, somebody interested can tell it, called resonance photoemission study. What you do, you remove 4f electron, put it in the 4d electron, put it in 5d, bring electron transition. Now you look at oxygen band. When the transition takes place, the oxygen emission goes up. So that way he has proved that there is a 4f symmetry in the oxygen band. You follow what I mean? Originally I said 4f electrons are localized. Now you find the 4f electrons sitting in oxygen band, where the bonding takes place. Okay, so that means the 4f can participate in bonding. Therefore, right. Completely transferred, right. It maintains 4f character, and the later on band structure calculations are revealed by coiling that there is indeed 4f character in oxygen band. That further proof later. So therefore, your 4f character oxygen band retains 4f character. Yeah. Yeah. Yeah, right. So therefore, this is a very interesting finding. Therefore, I'm going back to the question, what is the meaning of valence? Yeah. That's what I'm trying to say. That is what the assumption was till 1980s. Okay. That's what chemists would say. But if you are physicists, if you look at it, there is a 4f count. So where is it coming from? That is not coming from, there is no 4f electron in the localized orbital. There is something extended orbital that is mixing with oxygen by retaining a 4f character. Therefore, the question comes, going back to now the question, now you call cerium dioxide is mixed valent or tetravalent or mixed valent? Because as I started with the transparency, that is the measure of 4f valency, is measure of 4f count. Right? Now, what do you call this? You say 50% 4f electron, 0.5 4f electron sitting in oxygen band. Now it is 3.5. Is it 3.5? That question came up. Therefore, the question of the definition of valence was questionable for those rarer cases where there's a strong 4f hybridization, extended 4f electron. This is basically one of the really important conclusions. We did very extensive studies, even on cerium metallic system. These are the conclusions we have drawn. There is nothing like tetravalent compound. If you say valency, you define what do you mean valency? The number of 4f electrons or number of localized 4f electrons? You have to define. When you say valency, you cannot loosely, people are still saying that you have to define what do you mean. There is no cerium compound without 4f electron, including cerium tetrafluoride. I have paper and PR on cerium tetrafluoride. We have shown the same thing. There's a 4f count sitting on fluorine. So therefore, there is really no cerium without 4f electron count. Whether cerium dioxide, cerium tetrafluoride, you always something, whether either localized or outside. And if you really want to count as the number of 4f electrons, you will never exceed 3.3. This, by the way, Wellman did a thermodynamic calculation. He tried to publish physical letter, he couldn't publish it. Finally published physics letters. Very beautiful thermodynamic calculations. You arrive at that, thermoenergetically, you can reach only 3.3. By that I mean, you should have at least 70% of the time 4f electron with the respective cerium. It's a very, very important change in the concept of the valency or concept of errors. I thought I should say that. Okay. It does have implication, but I don't know if the chemists have taken note of that. I mean, they may lose say cerium dioxide still tetravalent. You define what do you mean valency there. If you define as the absence of localized 4f electron, that valency is fine. There are no localized 4f electron. No, chemistry defines the number of electrons participating in bonding, right? If you define the number of electrons participating, 4f is participating in bonding. There is a contradiction, right?
Very important. Iron. Nominally say iron. Electrons.
Yeah, right.
They form a hybrid oxygen atom. All these things are very relevant for chemistry. Nominally call it.
Yeah.
They know their things.
Yeah, right. Yeah,
Occasionally it happens with rare earths.
yeah, right.
But happens, that's
Oh, yeah. Okay, now when the research was going on 1970s and 80s, and people found much more exotic behavior. That for example, cerium aluminum 3, for the first compound, where they found out if you measure heat capacity as a function of temperature, there's a linear term here. You know, the linear term heat capacity contains, simple metals, two terms. One is linear term, gamma T. Gamma is a electronic coefficient related to density of states. Second term is a lattice term, gamma T plus beta T cube is the heat capacity. So, forget about beta T lattice part, it basically dominates the high temperature. Low temperature, what remains is only the linear term. Linear term, for example, a simple metals, you find for a copper metal, less than 1 millijoule per mole K square. In this case, you would find this compound is non-magnetic. As I told you, this also belongs to the same class of like cerium, cerium metal, and there is no magnetism at low temperature. High temperature is like magnetic. So you could find here that in this compound, the gamma value is 1.62 joule. It is more than 3 orders of magnitude larger than what you expect for a simple metal. This is a complete transformation of our knowledge. So this paper was published Solskjaer Communication, So those days today that people don't even hear of that journal, very unfortunate. Very important research published those days in Solskjaer Communication. Paper is published, rejected in PRL, you'll get Solskjaer Communication. I have published Solskjaer Communication. Anyway, this is a very landmark discovery. So you could see the linear term, which should be less than 1 millijoule, it is 1.62 joule in this compound. Okay, this is, I will come to the explain. This terminology is called, they call heavy electron concept, but discovered in 1975. There are other corresponding transport anomalies. I don't have time to discuss late from. Now the question, where is so let me slightly deviate a bit. In 1960s, 60s or 50s, so people have found, pure copper metal, this is the electrical distribution per temperature. You should go like this. To take really pure. However, if it contains small amount of iron impurity, you will find resistivity goes up. So there's a minimum resistivity. This bothered the community for quite some time. And then the Kondo from Japan came, he used second order perturbation theory to explain. What is that called? But high temperature, the local for magnetic electrons are free. As a good low temperature, they are getting bound by the conduction electron in metals. They get antiferromagnetic coupling. They become essentially non-magnetic. It's called Kondo singlet. This is the name of, honor of it, called Kondos. They form a singlet ground state. Therefore, you lose magnetism. So, and then whatever theory is that it really goes up logarithmically with decreasing temperature. There is a minimum in the temperature resistivity, which is signature of the binding of the formation of singlet ground state of the local moment. Initially started the magnetism. The question can say, I've been telling you at high temperature magnetism, low temperature no magnetism. That is where non-magnetism comes. At low temperature, depending on the temperature scale, they found a bound state. Therefore, when you start on the magnetism, losing that. Okay, so that results in message minimum. These are all the important characteristics of the delocalization, localization phenomenon. So, but it was believed when it comes to rare earths, the 4 of orbitals, you find that 1970, if you want, they exactly behave like this. If you look at the transport properties, they behave like copper. But okay, so okay, now how does it come about? Okay, so okay, now since you asked me here, see now when it comes to rare earths, as I told you, 4 of electrons are not as delocalized as the D. There is some degree of localization. At low temperature, they get delocalized. Therefore, they have a tendency to form a singlet ground state at every site. If we talk a cerium metal or any other cerium aluminum 3 or any compound, they form high temperature free electron, local moment, low temperature, they form a ground state. Therefore, at every site, you can form that so-called Kondo singlet state. They call Kondo lattices. There is a periodicity of the singlet ground state in the lattice. It's called Kondo lattices. This results in the renormalization. These are bare density of states. Because of the mixing of the 4f electron, they go out and come back, or hybridization or bonding, whatever terminology you use, you find their renormalization density of state at the Fermi level. These are questions which you ask. Therefore, you could find this is also called abrikoso-Sood resonance in honor of the people who discuss about that. They're huge, there's the density of state, that is the narrow band, actually very narrow band. It's called narrow band phenomena, different terminologies. Narrow band phenomenon is narrow, typically of the order of few milli electron volt or 10 or 20 of that order. It's not like several EV. So this is how the enhancement density of states. As a result of that, your linear term, it goes up. When you compare to copper metal, this is 3 orders of magnitude larger, therefore linear term is larger. That is how the electrons become, this is basically effective mass. The linear term tells you about the effective mass of the electrons at low temperature. When it goes up to 3 orders of magnitude, that means that effective mass has gone up. They become sort of almost immobile. Very loosely speaking. Am I right to use terminology? Very become electron, conductor electrons very mobile. This one is immobile. They hybridize with everything. They still remain immobile. Therefore, they become really narrow band. I mean, they remain narrow band. Okay, so therefore, they have become very heavy electrons. Okay, they are not supposed to move very heavy electrons. Only the contribution is to enhance the density of state because of the narrow band. Please remember that they are very heavy. I'm going to next statement, very interesting. And there are related associated Fermi liquid features. This is not really relevant at this moment. Okay, now another interesting aspect. When people are studying that, in 1979, the Steglish published a paper, a new compound, cerium copper to silicon 2. He found the same heavy electrons, which are supposed to be essentially mobile. See, if I find in this compound superconductivity, exactly opposite thing, which is not supposed to move. I'm putting very, very loosely. Okay, it becomes superconductor, 0.5 Kelvin. And he published this paper, he sent this paper to PR in the presence of strong polyparamagnetism. Polyparamagnetic terminology because, as I told you, high temperature is magnetic or low temperature is non-magnetic, enhanced susceptibility. So, therefore, the superconductivity in the presence of strong polyparamagnetism. So, this paper is in a very vague manner, the unexpected superconductivity, and then you could find that jump in the heat capacity. I mean, for the benefit of students, the superconducting transition, the jump which you expect is should be proportional to simple metals electronic coefficient, as I just mentioned. In these materials, as I told you, 3 orders of magnitude larger. The jump also scales with that. Therefore, superconductivity comes from the exactly same electrons which are responsible for a fermion behavior. Is it clear? Is it clear? So the delta C should be, I'm talking about student, delta should be proportional to electronic term, right? The electronic term. So, where in these materials, the electronic term is huge. They find the delta is also enhanced to 3 orders of magnitude. Okay. Like effective mass. Therefore, this is called heavy fermion superconductor. This is for the first time discovered. This thing is called superconductor comes. It's supposed to be unconfident superconductor. Even now, you'll see for same Steglish keeps publishing paper on cerium copper silicon 2. For the past 5 decades, there's so much exoticity. This compound not fully understood. There are many details. There is a very interesting background. It's an anecdote, I should say that. He was before with Dieter Ulleben, whom I have been mentioning in Cologne. Again, been recorded. But this statement made by Steglish to me. He sent that paper to PRL, paper got rejected. And he also knows who the referee is. I had a tough time to publish the paper. So the reason is that at the end of the PRL paper, he says that some samples show superconductivity, some samples do not show superconductivity. I welcome the community to sort of confirm it. Okay. And the referees did not believe, oh, what is saying the magnetism in your material. Magnetism can result in huge jump in heat capacity. That is a typical characteristic of magnetism. So you are seeing some muck. So I rejected the paper. Even today, if you see the paper, he is asking community to welcome. Sort of, we would welcome a confirmation by other workers of our conclusion that cerium copper silicon is intrinsic superconductor. You send the paper to any journal, your referee will throw the paper. Am I right? right? You also are not sure. But those days, I think things are welcome. Even if you, as long as you do honestly do experiment report, people used to welcome, and it turned out to be pioneering work. And later on, people confirm, yes, it is true. It is correct. And later on, at least now today, at least 1 dozen materials which are heavy fermions superconductors. Because you allowed this paper to publish in PRL. If I am referee, I don't accept it, there is no way the field can progress. This is what a very important lesson. Sometimes we should be a little bit more pragmatic in our approach. Okay, there is an interesting history. Unfortunately, I don't have time. He was with Ullaban before. He was studying polycrystalline material. He found that superconductivity at 0.3, some sample again, no, not on all samples. The Meissner fraction, which I don't know in detail, the fraction of superconducting sample is something like less than 1%, 0.1%. He found that. And Ullaban, being the boss, he did not want to make it a part of the paper. No, what do you mean by some sample shows? He's a very thorough physicist. I know Ullaban very well. So you should be confirmed, then only you can publish it. But Stegler did not like it. He put it a footnote in the paper. The paper was published J-square physics B. Okay, it's today the journal vanished. That is a high TC superconductivity was reported, Wilder. The journal vanished. It's called European Physical Journal B. There's a footnote, you will find it. In fact, you will find here. In fact, he gives a name, which I gave sample to somebody, he found superconductivity, somebody else did not find. So that is what he says, the footnote. So he left this place, he moved to Darmstadt and took the study seriously. That is, he published the founder UK confirmed. He confirmed this, he published a paper, PRL. You know, it's called serendipity. What is the terminology used? Was current serendipity? It's not serendipity, right? Serendipity. You know, something you find, if you believe in it, is a very important lesson for youngsters. You should pursue that. As long as you do experiment honestly, you should not leave it. You know, there one of my postdocs, I was very angry. I don't want to mention name. He normally I go and keep track of data in the lab. Now, one of the postdoc, he recorded data, and something unusual he found, a small glitch. So he wanted to show it to me, and when I saw the screen, it was there. When he printed out, that glitch vanished. Okay, I asked him, I said, sir, there's nothing. I deleted it. I know, why are you deleting it? Why are you deleting it? You should not delete the data. You should repeat the data 3-4 times. There's something around thermometry, something of the instrument, something of sample. Make more sample, repeat again, because you may miss interesting physics. If Stiglitz has left it at that stage, probably probably wasn't discovered for another 1 decade. You never know. They're all very important lessons. So whatever this, I just want to tell you that how serious people, Germans are very serious. I mean, when they will take up something very, very serious, bring it to a logical conclusion. They're very thorough. I worked with a German professor. You will not allow one line to be added without any basis in Kindle. Very difficult to push a paper to send it to a journal. I used to get angry those days. Now I realize the value. You have to be very thorough. You have to be correct and precise. Okay? And you have to be honest. That's absolutely important. Okay, so sure. Okay. So anyway, I don't want to go into details. There are many interesting aspects of thing, and I don't want to go into the detail. Okay. Now the only important thing is that you can modify. I told you at low temperature you have non-magnetism. You can tune you can make it magnetic. The one of the important aspects toward the literature study the magnet. At this end, you have magnetism. This are ordering temperature as a function of the coupling strength of the 4f electron conduction band. At high temperature, at high large value, basically large hybridization, large bonding, you have a intermediate valence. At weak bonding, you have the stable valence, and you can go from stable valence to strong hybridization line. In between, where you are losing magnetism as a function of coupling, the very exotic phenomena are discovered, quantum critical points, called quantum critical point effects. This is one of the things which are attracting a lot of attention. Anyway, with that, I leave cerium out, and there are many ferromagnetic control lattices. They are again surprising, non-ferromagnetic lattices, just somewhat insulated. The basic question remains unsolved. How does 4f radial extension look like in light rares? Exam cerium. We see only the consequences of extension of 4f orbital properties. So this question is more and more normally you find. Okay, now I will point out one excitement when it comes to heavy rare earths, which made a difference to the field. Now, as I already mentioned, gadolinium, the radial extension is a radial extension of 4f orbital. It is deeply localized. One may expect that it's a dead vegetable. It's nothing interesting. It's going to be so for decades till recently. And we found and some anomalies in this compound which mimic some cerium. Bhaskaran was there. I mean, there's a conference, Howard conference. Zlatis organized, every year is organized. 2 years we were together, same conference, very beautiful seashore, beautiful island. And I raised a question. I was invited to give a talk. Do we understand electron correlation effects in gadolinium-based intermetallic compounds? That paper was very well received because full of theoreticians. I thought I'd report the results there. Because we have found for the first time very novel results. I'm going to show what it is. And this question still remains. And now slowly people are trying to realize, yes, there are problems. Okay, what is the result? And let me not go into crystal structure. Okay. Only one thing I want to tell you that one family of compounds, only 5 minutes left. These are one family of compound AlB2 derived hexagonal compounds. And we study very systematically. If you look at it, neodymium here, look at this ferromagnetic like. Okay, and the other ones are antiferromagnetic. You see an anomaly here. And we have shown here in neodymium also your 4F is participating in bonding. Unlike in other cases, there is no bonding. So 4F participating in bonding can change the magnetic characteristics. It's a very clear-cut example. We published a paper, few papers in physical review B to establish particular point. We have more examples now. So this is one of very exceptional. Let me leave it as it is. Let me go to gadolinium. There are more details. Let me not worry about. Look at gadolinium. Okay. So, okay. Let me look at the electrical disturbance from the temperature for any metal. It mainly two contributions. One is the spin, due to the ion defects in the lattice called lattice defect contribution here, which is it's a constant spectrum of temperature. Other one is the spin disorder contribution. This is a paramagnetic state. This is a magnetically ordered state. And the spin disorder contribution, you are losing when the system orders magnetically, when there is an alignment of all the spins. So this basically what I told you, De Jon's originally said. This particular number scales with the De Jon scaling. It's the number. Okay, these are normally expected behavior. In this kind of situation, a normal behavior like this, what I observed for gadolinium was believed to occur for gadolinium or heavy rare earths. I mean, apply magnetic field, you don't expect much change by the presence of magnetic field. I will not go into the details. Somebody interested, I can discuss later. So this is what you expect of gadolinium. In contrast to that, okay, you will find in cerium compounds, this, as I told you, is what you find. The resistivity is a minimum here. Okay. Of course, if you have a large number of your cerium ions and lattice, you will see a decrease. That is called coherent effects. Don't worry about it. What is important is that if you have heavy fermions, you will see a minimum here. If you see a Kondo effect, you see a minimum here. Okay. So in this compound, we observed for the first time the breakdown of this rule. Which rule? This rule. This is the textbook material. This rule is broken down for the first time in 1988. And we reported even in this compound, we see a resistivity minimum here. Okay. Even if dilute by yttrium, you still find it here. Even heat capacity is also quite large here. So it behaves like a cerium, heavy fermion compound. However, it is not heavy fermion. We can prove by other methods, not heavy fermion. We found many other compounds in this family of behaving similarly. And there one set of family where the temperature coefficient resistivity is negative, where that means minimum is somewhere here at high temperature. So even some of the heavy rare earth compound where you don't expect anomaly, they behave like cerium on the face of it. Okay. So when I sent the paper, the first paper in PRL got rejected. He said, where is the theory? Okay. So I cannot say results must be wrong. Later on, it is proved our results are correct. Okay. Anyway, so now subsequently, I found another family of material with the PRL. In this family, you could say very clear evidence for a minimum here. Samarium, neodymium, dysprosium, terbium, everywhere you find minimum. Only thing people are not studied very thoroughly. On the one hand, it behaves like a localized moment, on the other hand, Kondo-like, but it is not a Kondo effect. It took toned of decades to, the basic message was, I was trying to propose in some normal, I put that here, rare metallic compound, there is an additional T-dependent contribution resistivity in the paramagnetic state, as the magnetic ordering is approached. It keeps increasing, scattering contribution increases as you approach long-range magnetic order, sometimes leading to Kondo-like minimum. These were not realized in literature. So this was theoretically taken up after 20 years by a very well-known group, C.D. Badista. You must be knowing C.D. Badista. he picked up, look at our work, he was motivated by our work here. He says he produced a theory that in the event there's a geometrical frustration. By that geometrical expression, I mean that if you have a triangle, if you put a magnetic ions here, if you ask them to ferromagnetic, it's easy. But if you ask them to antiferromagnetic, this fellow will not know what you should do. This fellow will get frustrated. Same thing with the tetrahedra here. So they will create, it will be very, very problematic. So this leads to frustration. It's called geometrically introduced frustration of magnetism. Let me leave it like that. He produced a theory that a combination of geometrical frustration on magnetic moment. It is not a frustration due to anything else. The geometry, crystal structure does not favor magnetic ordering for some fraction of the ions. So it can lead to a resistivity, meaning it's a new physical origin of that. Then we took 20 people. Asked me for a theory in 1998. How can I produce a theory? Paper got rejected. Anyway, later on, I published one more paper. So what I want to say, very surprised for our was the first work of that kind of literature. Now some more theoretical groups have picked up this work and produced various. They look at this paper here, cited for our work, published more papers of similar type, and they are getting cited in this field. So okay, so this is one aspect. I'll take a few minutes. Most important thing, this is the paramagnetic state. Now, in the magnetically ordered sort, although this comes the fundamental breakdown of first breakdown fundamental law of solid state physics. Let's look at total resistivity. Total Hall resistivity should be a textbook will tell you that a normal metal anomalous spot. Okay, this is a normal conduction electron. This is from the magnetic electrons normally. But in this compound, we find that there is an additional contribution of Hall resistivity propping up here and then settles down. So we propose that it cannot be understood within the existing knowledge of solid state physics. So this work was left as it is. We published Physical View B, and then now there are proposals. People are 10 years ago, the concept of magnetic fermions was proposed, where you neither classify ferromagnet nor classify antiferromagnet. You have textures of the magnetic moment. In other words, it's something like nanometric scale you find everywhere in the material. So this can cause that kind of extra anomaly. It's called topological effect. I will not explain the term what is topological. The new concept in solid state physics, topological effect, which can come from this kind of phenomenon. This is being formally proposed on the basis of studies on manganese, silicon, iron, cobalt, silicon in 2000 by German group in 2009, 2010. And it is now proven, see that additional contribution here, this is called topological contribution. Somebody interested in question our session can what is topological? It's a new phenomenon in quantum mathematics physics. So these are potential applications, spintronics, next generation information storage due to ultra threshold for current driven motion, large storage capacity, high speed. And this, the reason is fermions can be created, manipulated, and read with the real current densities. Domain wall track, racetrack memories, fermion based laser velocity is one of very major topics of research quantum physics. I just want to tell you the work which published in 1998 was repeated by Tokura's group and they published in Science. It's very wild. They don't even cite properly. I contacted the editor and they allowed me to publish. You look at this. This is basically the thing. Of course, now they find magnetic fermion. That's a different point. And it's the same thing here. Extra contribution Hall resistivity. So I wrote a letter and they asked me to publish a editor, basically trying to say that our work turns out to be the first work in the field of topological Hall effect. So therefore, even before others have reported, we have reported. This made a difference to the field. That's what I want to say. I've shown some example where we made a difference to the field, some other works. Therefore, okay, I can keep on speaking like this. I'll come to the conclusion of my thing. There are many things I can keep talking. I should skip that. There are many heavier earth compounds. We see novel and more novel phenomenon. And some talk I can get off is relevance to get off physics and take home messages is that the field of electron research continues to be rich even after 6 decades. Potential applications avenues increasing. Participation of 4F chemical bonding, unlike what was believed earlier in light rares, leading to many exotic phenomena. Valency definition is, one has to be careful about the definition. Novel Kondo-like minimum in resistivity for normal rares, now called even for so-called stable valence system. Unexpectedly, theories are getting evolved now after 2 decades. Topological Hall effect anomalies very early even before it was formally discovered, even for discovered nanomaterial. So non-anomalies, non-magnetic, many normal electrons were proposed. This is basically a broad overview. I'm sorry, I don't know whether I can convey the message. Basic point is that despite our own difficulties, this is a very vast field, very heavy competition. Despite our own difficulties, from time to time, we are able to found some interesting phenomena, which later on picked out by others, very satisfying. Thank you very much for your attention.